Hey everyone, Cowboy Bry here again. Thank you, Rajiv, for that compelling introduction to the mathematics of case-based entropy. We need to shift now back to this issue of why, though. Why would we study this stuff? We've tried to make the case that case-based entropy is a measure of the diversity within a complex system that incorporates both species richness, that's the number of cases, frequency, and the evenness of species abundance, that is the diversity of types, be they discrete or continuous, with this relationship between an equiprobable distribution where all cases are possible and the actual distribution itself, which comes from empirical inquiry. So quickly, why? Why is this measure useful? Synonyms for diversity are sufficient. Inequality. Inequality is in many ways a measure of diversity. Economic diversity, cultural diversity in systems. You can also talk about species diversity in an ecological community, which is where this work initially comes from anyways. The diversity of information in cybernetic systems. This builds off the work of Shannon into all the various cyber infrastructure mechanisms that run our global society today, to the diversity of major and minor trends in longitudinal data. Think about all the different type of longitudinal data, consumer choices, the diversity of consumer choices, health outcomes, health trajectories, well-being trajectories of communities, the trade diversity of a country, network diversity in terms of node diversity, hub diversity, different types of clicks, connections, links, and so forth. And then the diversity of complexity in complex systems. All of which takes us to the issue of examples, empirical examples, as to how this measure actually improves our understanding of the diversity within systems. You see up here a simple graph probability distribution of household income in the United States for 2012-2013. Here we have 41 different diversity types, right? Going from under $5,000 to $200,000 and over. If one explored this distribution using regular statistical terminology, n equals 41 would be used to compute the mean, median, mode, skew, and so forth. That is not, however, what case-based entropy is doing. In case-based entropy, the 41 types is not used to compute perfect diversity. Instead, using the formulas that Rajiv introduced in our basic mathematical introduction, we compute the Shannon entropy value, and it comes out to be 31.21. 31.21 equiprobable types are necessary to explain the total diversity of information in this system as concerns economic diversity within the United States 2012-2013. With this equiprobable type computed, we use that as our denominator, which allows us to convert these actual distribution breakdowns in terms of percentages, and it's that gives us the scale-free nature that Rajiv was talking about, that allows us to not only compare distributions one to the other, say the distribution of diversity in a variety of country economic systems, but also allows us to compare the distribution of diversity within the system for particular segments relative to others or the total. For example, with our denominator determined, we go back to our original 41 types, right, up here, relative to the equiprobable types, 31.21, and we find that, for example, type 1, under $5,000, which comprises roughly 3.32% of all cases in the sample, has a diversity contribution of only 3.20. In turn, when we do a larger combination of types, for example, here under 5,000 to roughly 64,999, we find that this constitutes almost 60% of all cases in the sample, which are household incomes, and that for the first 60% of all household incomes, the percentage of diversity contribution explained is only 41.03%. That turns out to be a rather interesting insight, but before we get to it, let's go up here and talk a bit more about the difference between thinking about things as equiprobable distributions versus our normal notion of a probability distribution function. On the top is the distribution we saw earlier. Down here, however, is that distribution reframed in terms of case-based entropy. The x-axis provides us the cumulative percentage of diversity accounted for in the system as a whole based on the notion of equiprobable types. And that goes from 0 to 100. Then we also have the cumulative frequency of cases, which again goes from 0 to 100, giving us our scale-free nature. What's interesting is that when we plot the graph for income distribution, it passes through this segment of the graph, which has to do with what we call the 60-40 rule. And what was interesting was income was not the only system that we found this general notion of 60-40 to be true. We studied an additional set of systems from galaxies all the way down to genes and found that indeed this notion of some type of 60-40 relationship existed, where 60% or more of the cases in the system comprised 40% or less of the total diversity contribution. This led us to think that there might be some type of phenomenon that exists as an underlying pattern in a variety of complex systems. And you can see here the systems we examined as plotted as a basic probability distribution, all of them taking this skewed right formation. And then when plotted on our case-based entropy graph, all of them moving through the 60-40 region. Again, suggesting that it seems for some reason, which we're not entirely sure yet, that there is a restriction on the diversity within many complex systems. And it's that sort of insight that the case-based entropy measure allows through this scale-free comparison of systems. And it's with that I turn it over to my good colleague Rajiv, who's going to show how this notion of restricted diversity and case-based entropy apply to three of the most fundamental distributions of energy.
Okay, so after those 8 different complex systems that Brian talked about, we tried to see if we could apply our diversity measure, the case-based entropy, to some other distributions from physics. This is when we started working with Anna Wilson, who is our friend and colleague through the ESRC seminar series. We started some discussions on applying the case-based entropy calculation for the 3 classical energy distributions for subatomic particles, namely the Maxwell-Boltzmann distribution for ideal gas, for the Bose-Einstein distribution for bosons, and the Fermi-Dirac distribution for fermions. As of now, we are able to get these different diversity curves of CC versus C for each of these cases, and we are trying to understand at this stage what this really means in terms of comparison, and why is, for example, the Maxwell-Boltzmann in one dimension giving us a lower value of percentage diversity contribution as compared to the other cases, like, for example, the Fermi-Dirac, for the same choice of cumulative distribution. And so this is where we are, and we hope to kind of unravel what the case-based entropy measure means for the ideal gas, bosons, and fermions. And also, I have to say, we tried to explore the variation in these curves for several different temperatures. An interesting aspect that we saw was, first of all, even though the original energy distribution for each of these cases is completely out of scale for each of the temperatures, in the sense that we actually cannot plot any of these density functions on the same graph because of the huge variation in scales. So one of the biggest advantages, for example, of the case-based entropy measure is that we can plot all of these density functions in terms of the diversity contribution on the same graph and compare them, even though we can't plot the original density functions. And we also saw that for the Maxwell-Boltzmann as well as the Bose-Einstein cases, the entropy case-based entropy curves were independent of temperature. Well, it's not very surprising because it's already well known in the physics community that a temperature change just changes the scale of these distributions. However, for the Fermi-Dirac distribution, we saw that for each temperature, we got a different case-based entropy curve. That's simply because of the Fermi energy that the electrons or fermions have to overcome in order to start becoming more and more diverse in terms of equiprobable energy states.
So that brings us to the conclusion of our introduction to case-based entropy. But Ajeev and I hope that you will check out more of our publications as found on our site, Case-Based Complexity.